Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. 27% of the energy density in nickel-based lithium-ion batteries isn't accessible, which could provide many EVs with 38% more range. That's because nickel-based lithium-ion batteries are capable of operating at up to 4.7 volts or more, but EV makers restrict the voltage with battery management software to around only 4.2 volts. They do that because there's greater reactivity and therefore faster degradation at higher voltages, which reduces the number of charge-discharge cycles that a battery can last for. Battery scientists and engineers have tried to solve the degradation problem with chemical and materials engineering, but most solutions have had limited success. However, a new paper from the University of Chicago has been able to achieve a 21.8% increase in energy with long cycle life through a small change to the cathode design. The catch is that Tesla is currently the only company in the world with the technology stack to make it work at scale, which is their dry electrode coating process. So today I'll walk you through the cathode design, why it works, and in the long term, what it could mean for Tesla. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. Let's start with how high voltages cause degradation in the cathode of a lithium-ion battery cell. In this video, I'm going to be focused on the nickel-based cathode materials that are used in longer-range EVs, rather than the iron-based LFP batteries that are commonly used in shorter-range vehicles. I'll explain why in a moment. The cathode film of a lithium-ion battery cell contains three materials. First, the cathode particles, which hold the lithium in a ceramic oxide crystal framework that's usually about 80 to 90% nickel and 10 to 20% manganese, aluminum, and cobalt. Second, conductive carbon particles form an electronic matrix to get electricity to and from the cathode particles. And third, a polymer binder that holds the cathode film together like glue. As the battery charges, the voltage of the cathode increases from about 3 volts at 0% state of charge to 4.2 volts at a typical 100% state of charge. The higher the voltage, the more lithium ions are forced out of the cathode and are pushed to the anode. At 3 volts, the cathode structure is packed with lithium ions, and at 4.2 volts, about 73% of the lithium in the cathode has been transferred to the anode. The exception is LFP batteries. That's because compared to a nickel-based cathode, about a third more of their crystal structure is filled by structural atoms instead of lithium atoms, and so almost all of the lithium can be removed and they still maintain structural and chemical stability. That means there's minimal headroom to increase the voltage further by the time most of the lithium has been pushed out at around 3.6 volts, which is usually considered 100% state of charge for LFP batteries. Getting back on track, between 4.2 volts and about 4.5 volts, the nickel-based cathode particles and conductive carbon particles start reacting with the electrolyte to produce a variety of solids, liquids, and gases that reduce the cycle life of the battery. Then, above 4.5 volts, the degradation becomes more aggressive. The nickel-based framework of the cathode starts dissolving into the electrolyte, which poisons the electrolyte solution, and the cathode crystal starts cracking and collapsing, which further accelerates the dissolution. In the past, battery scientists and engineers tried to prevent those degradation mechanisms with improved electrolytes and better cathode designs. Those solutions have provided great improvements in cycle life and small increases in energy density for some high nickel cells. But for the most part, 27% of the lithium and therefore energy still remains out of reach. Next, let's do a quick refresher on the basics of a typical wet slurry coating process versus the dry coating process that Tesla uses. That's because it's critical to understanding the University of Chicago research paper. A typical wet coating process involves mixing the cathode powder, carbon powder, and a dissolvable binder powder with a liquid to form a slurry. That slurry is coated to the cathode foil and dried in an oven. As it dries, the binder comes out of solution and coats all of the particles to hold them together, forming a cathode film. Tesla's dry process also starts by mixing cathode powder, carbon powder, and a binder powder, but the binder used is PTFE, also known as Teflon. When PTFE is exposed to shear forces and heat, it fibrillizes like bubblegum into spider silk-like filaments that turn the powder mixture into a kind of dough, which is heated and compressed to form a cathode film. No drying required. With that refresher in place, let's look at the paper mentioned in the introduction by Zhang et al. Titled Dry Electrode Architecture Designed for Pushing Energy Density Limits at Cell Level. The paper starts by describing mechanisms that could be contributing to the high voltage degradation problem. Figure 1A shows a 125 micron thick cathode that was formed using a wet process. Figure 1B shows a cross-section of that cathode using X-ray diffraction, and there are 4 spots highlighted and numbered, which are pinpointing specific cathode particles. The image is a point-in-time snapshot of a series that was captured using video, and the different colors indicate changes in the crystal structure that occur as lithium ions leave the cathode during charging. That time series data is graphed out in Figure 1C, where the progression of the crystal structure changes during charging can be seen more clearly. Below 4.2 volts, the crystal structures of the particles progress in unison. Then, above 4.2 volts, particles 1 and 2 diverge from particles 3 and 4, showing differences in the crystal structure, indicating differences in lithium content. Differences in lithium content mean the particles are losing lithium at different rates, which means the particles are experiencing different voltages. So what the graphs are showing is that above 4.2 volts, different regions within the broader cathode film are experiencing different voltages, which in turn means different degradation rates. So what's going on here? As I said a moment ago, in a wet slurry-based coating process, the binder is dissolved into solution and coats all of the particles as the solvent dries, holding the cathode film together. What I didn't mention is that the binder is an electronic insulator, which can interrupt the flow of electrons through the cathode film. So different regions, and therefore particles within the cathode film, have greater or lesser access to the electrons that drive chemical reactions. That is, the poor electronic network created by the wet process is the core problem and weakest link in the electrochemical chain. So it's no wonder there's been limited success at solving high voltage degradation through improved electrolytes and better cathode designs. While those solutions might improve durability up to, for example, 4.5 volts, the reality is that in a cathode running at 4.5 volts, some of the individual cathode particles might actually be spiking up to 4.8 volts or more, leading to rapid degradation despite the improved durability. That, in turn, means the process and engineering involved in manufacturing the cathode needs to be fixed before chemical or materials-based solutions are applied. If the cathode film could be manufactured so that the insulative binder didn't get deposited between the particles and block electron flow, it would lead to more uniform reactions, eliminate pockets of extreme voltage, and reduce degradation in the cathode as a whole at higher voltages. However, some of you may have noticed that there's a few missing pieces here. For example, in Figure 1C, why do the differences in electrochemical activity only show up above 4.2 volts? And even if the conductive carbon matrix could be improved to prevent cathode particles from degrading, it doesn't solve for the fact that above 4.2 volts, the carbon itself would still react with the electrolyte. To resolve those questions, let's take a look at the solution proposed by Zhang et al. And its performance versus a conventional slurry-coated cathode. The paper proposes replacing the carbon particles in the conductive carbon matrix with a more string-like carbon material, then coating the binder over those strings like electrical sheathing. That would solve three problems at once. First, the binder sheath would insulate the carbon from reacting with the electrolyte. Second, a string-like carbon material would have lower surface area than carbon particles. Third, by applying the binder around the carbon strings rather than between the carbon particles, the binder would no longer create electronic resistance in the conductive carbon matrix. When I first read these design principles, my gut instinct was that the solution they were about to propose would either require a tedious manufacturing process or expensive materials. But shockingly, their solution requires neither. First, use the dry electrode process that Tesla claims they've now solved. Second, replace the carbon particles with vapor-grown carbon fiber, or VGCF. At a high level, that's it. Pretty simple. Let's take a look at the cost and how it works. At a molecular level, vapor-grown carbon fiber looks like a series of nested waffle cones, and in terms of manufacturing cost and complexity, it's between carbon nanotubes and carbon fiber. At scale, it would probably cost around $100 per kilogram, and would probably only make up around 2 to 4% of the cathode by weight. If that's correct, it would only add about $1 to $2 per kilowatt hour, or a 1 to 2% cost premium over conventional battery cells. However, factoring in the 21.8% energy density boost it could provide, the battery cells would end up being 20% cheaper. But we're getting ahead of ourselves. How does the proposed solution actually work? When vapor-grown carbon fibers are used in the dry electrode process in place of carbon particles, the shear forces of the mixing cause the long PTFE filaments, shown here in yellow, to get twisted up around the carbon fibers, which are shown in black. Then the carbon fibers naturally form a chemical bond with the PTFE. That results in a binder-sheathed carbon fiber that's insulated from reacting with the electrolyte. It's not completely insulated because the binder doesn't perfectly cover the carbon, but as we'll see in a moment, it helps tremendously. As a side note, I imagine carbon nanotubes could also be used, and they might actually be cheaper. That's because although they cost 10 times more and have greater surface area than vapor-grown carbon fiber, they could be used at dosages of maybe 20 times less. However, I don't know if they'd entangle or bond with the PTFE as effectively as vapor-grown carbon fiber. Even if not, they would likely still improve high-voltage performance in wet or dry-coated cathodes by creating a more continuous electronic network with less reactive surface area than carbon particles. Next, let's check out the test results of the proposed dry-coated cathode versus a wet-coated cathode. The images on screen are colorized cross-sections of cathode material. On the left are Zhang et al.'s proposed dry-coated cathode design, and on the right are a comparable wet-coated cathode design. Images A and B show cathode particles in red, the carbon binder matrix in dark blue, and pores in light blue. As you can see, there's less porosity in image A, indicating better physical connectivity. Images C and D highlight that connectivity more explicitly. The cathode particles are in gray, and you'll notice multicolored pixels between them. All pixels of the same color share an electronic connectivity network. Image C for dry coating is mostly pink pixels, meaning electrons can travel almost anywhere in the electrode through the conductive network without having to pass through poorly conductive cathode particles. Image D for wet coating shows many colors and large black voids, meaning it's difficult for electrons to percolate through the cathode film. Image E and F are where it all comes together. The colors indicate current density, ranging from low current density in blue to high current density in orange and red. Image E for dry coating shows that most of the cathode particles are blue and therefore barely used as a current pathway. Meanwhile, the conductive carbon binder matrix is mostly shades of orange, showing that it's the preferred electronic pathway. Image F for wet coating shows cathode particles that are mostly light blue to yellow, indicating heavier use of the cathode particles as an electronic pathway. Additionally, the carbon binder matrix contains more yellow and green than image E, so it's carrying less current. What all this means is that the dry-coated cathode directs most current through the preferred low-resistance carbon binder matrix, and any current that flows through the cathode particles does so relatively evenly. That's as opposed to the wet-coated cathode, where the carbon binder matrix is electronically fragmented, forcing uneven and heavy use of the inefficient cathode particles as a current path, which of course leads to the variations in voltage and therefore degradation that we saw earlier in the video. But why do the voltage variations begin to appear above 4.2 volts in the wet-coated cathode? At higher voltages, the cathode particles, which are being used as an electronic pathway but shouldn't be, begin reacting with the electrolyte and form a thick cathode electrolyte interface, or CEI, that's an electrical insulator. That isolates some of the weakly connected cathode particles and forces more current through the well-connected particles, which increases voltage differences between particles and causes them to degrade more quickly. Meanwhile, the current moving through the exposed carbon particles in the wet-coated cathode reacts with the electrolyte at voltages above 4.2 volts, driving further degradation. For clarity, on screen is the high-voltage degradation pathway of a wet-coated cathode. As for the proposed dry-coated cathode design, the carbon binder matrix is highly conductive and well-connected, which avoids using the cathode particles as a current pathway. That, in turn, prevents thickening of the cathode electrolyte interface, which means reactions remain uniform throughout the cathode and avoids voltage spikes. Furthermore, the carbon binder matrix functions like insulated electrical wire, which prevents the carbon from reacting with the electrolyte. This combination dramatically reduces high voltage degradation. Again, for clarity, on screen is a summary of how the dry-coated cathode design works. So how well does the proposed dry-coated cathode perform? Pouch cells using a high-nickel NMC811 cathode and graphite anode were charged to 4.55 volts and retained 78% of their capacity after 1,000 cycles. That cycle life is roughly in line with typical high-nickel battery cells. However, at 4.55 volts, the dry-coated cell would provide about 21.8% more energy density and therefore EV range than a battery cell that reaches 4.2 volts, and it equates to 317 watt-hours per kilogram of usable energy density compared to the 260 watt-hours per kilogram of the current Tesla 4680 cell. A 21.8% energy density increase is, of course, well short of the theoretical 38% possible at higher voltages, but that may never be possible because the cathode dissolution accelerates above 4.5 volts. With that said, the 21.8% energy density increase was reached with a basic cathode and anode chemistry, NMC811 and graphite. Even a small amount of silicon, which is standard in many high-nickel battery cells, would add about 10% to the energy density. The next question is, will Tesla adopt the cathode design proposed by the team at the University of Chicago? There's no way to know, but I can provide some further context. First, Tesla has probably known about the design for quite some time. That's because there's deep cross-pollination between Tesla's Maxwell acquisition and Shirley Mung's lab at UC San Diego, going back at least 8 years. UC San Diego was one of the teams involved in the paper, and Shirley Mung was listed as an author. That lead time increases the odds we could see the high-voltage cathode design in the next 3 to 5 years, because it often takes over a decade for these innovations to reach commercialization. Second, Tesla hasn't yet started using silicon doping in the 4680 to increase its energy density. That's likely because it would add complication during the critical early ramp phase of the 4680 production. But it could also indicate that they plan to take another pathway to higher energy density, such as by increasing the voltage. Third, on that note, given the fully dry 4680 ramp has just begun, I'm not expecting major chemistry changes in the next year or so. After that, when or if they do decide to use a high-voltage cathode design, they would likely take an incremental approach to mitigate safety and performance risks. So we wouldn't see a 21.8% energy density boost in one cell generation, but more like 5 to 10% over a series of generations. Fourth, for me, the biggest unknown as to whether Tesla could deploy a high-voltage cathode design is that there's likely an engineering gap between what was described in the research paper and Tesla's manufacturing realities. For example, Tesla may have had to use other binders besides PTFE to get the fully dry 4680 to work. I don't expect that would be a showstopper, but it could add years to the commercialization process. Fifth, Zhang et al. Used single crystal cathode to significantly increase the cycle life of their pouch cells. Single crystal cathode is more robust than typical polycrystal cathode material, but it's slightly more expensive. The combination of vapor-grown carbon fibers and single crystal cathode might add $5 per kilowatt-hour to the battery cost, roughly 5% more than a typical battery. With that said, although using single crystal cathode is an industrially acceptable shortcut to increasing cycle life, which is likely why the researchers chose it, there are other ways to increase cycle life that could be more cost-effective, such as better cathode designs and improved electrolytes. For example, Tesla could use some of the electrolyte additives developed by their research partner, Jeff Dahn. Those additives would essentially add no cost, but could easily match the 50 to 100% cycle life improvement provided by single crystal cathode material. In summary, thanks to Zhang et al., we now have a better understanding of what's actually limiting the voltage of high-nickel lithium-ion batteries, and an elegant engineering solution to access higher voltages. It could be the breakthrough that mass-produced liquid electrolyte batteries have needed for years to reach energy densities significantly above 300 watt-hours per kilogram. With one minor tweak to the conductive carbon material, it could eventually lead to around 20% higher energy density from battery cells with no substantive change to the chemistry, which could also mean cells that cost 20% less per kilowatt hour. And that's before factoring in any improvements to the anode, which could easily add around 10% to the energy density, leading, in the long term, to around 340 watt-hours per kilogram of usable energy density for Tesla's 4680 cells, as compared to 260 watt-hours per kilogram today. Overall, even if there is some critical drawback that I've missed, the research paper is easily one of the most interesting and insightful papers that I've read in my 6 years of running this channel. so I highly recommend reading it if you're a battery geek. It rewrote and thoroughly upgraded my understanding of what happens in lithium-ion batteries at high voltages. It also confirmed what I've been saying for 6 years now about Tesla's dry battery electrode process, that the first principles benefits of eliminating the solvent from the electrode coating process could pay huge dividends in the future. As the paper points out, the full potential of dry electrode technology remains unexplored. That's because the dry electrode coating process is brand new technology, so there are decades of innovation ahead of us. On that note, I only focused on increased voltage in this video, but the paper also provides insights on other ways to increase energy density, such as by making the electrode thicker and increasing the proportion of active material used in the cathode film. That's why the eagle-eyed viewer might have noticed that the electrode they tested in Figure 1A was 125 microns thick, which is around 50 to 100% thicker than a typical cathode. But that could be a topic for another video if you're interested in a sequel to this video. As always, please consider supporting the channel with the links in the description, which now also includes a referral link for Signature Solar. If you use that link to purchase home battery or solar equipment, it nets me a small percent-based credit, but that can add up on a large purchase and it really helps the channel. On that note, a special thanks to my YouTube members, ex-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.